Welcome back, everyone. Back to the MCAT grind. It's Biochem Chapter 4, Carbohydrate Structure. Carbohydrates is one of the lower yields based on Kaplan, but you will see this a lot in the passages, so it's good to get familiar with all the different carbohydrate chains, and they'll come up in passages even though they're not the main focus. It's just good to get them familiar with. Now, carbohydrates, by naming, you can tell by the prefixes triose, tetrose, pentose, so on, based on the number of carbons. So that's straightforward. And you name them with a D or L in front of them based on the OH at the bottom. So if the OH pointing to the right is dextrorotatory, so D. If it's pointing to the left, is levorotatory, so OH to the left. So yeah, we have aldose and ketose based on the most oxidized part. So if we take a look here at D, fructose, the most oxidized part is C carbonyl here, but additional with the C on the other side. So C on both sides of this carbon, so that means it's a ketose. See, there's C on both sides of a carbonyl carbon. Whereas here, the CHO, C is only bonded to the double bond to O, and the other side is H, right? So that is an aldehyde. So that would be an aldose. Aldose would be the carbonyl carbon bonded to H on one side and C to the other. Ketose is C to either side of the carbonyl carbon. Now we have our cyclic chains. In our cyclic carbon, if we have a cyclic carbon, we want to go from the Fischer projection to the Hathworth projection by bringing the O here all the way to the other side and then form that bond. So what we do here, we turn CH2OH into the left side and rotate all of this forward down. Then we turn this whole projection down this side. Then what you do is notice the OH on the end. If it's facing the same side, both going to the same direction, then it will be B, beta anomer. Anomer means an epimer, which is happening on the last carbon over here. Epimer basically is a when you have two carbons, they are just different. You remember from, what is it called? The Kahn-Ingold formation. You have R, R and S formation, that's right. So remember turning to the R and turning to the S. At the chiral carbon, if they're opposite, then that's an epimer. And anomer is one specific for it based on the anomeric carbon right over here at the end, at the last carbon over there. Because the OH can be turning up or turning down. When it's turning to the same way as the CH2OH, it's B anomer, beta, and you can think of B as in BAME side, just like how we have cis and trans from the organic chem. Cis is denoted with Z, same side, and the alpha formation. So I'm gonna change this up. Alpha formation is opposite side. Think about A, because A is trans, so it's E formation, right? Opposite side. And beta anomer is preferred because when you do the projection, OH filter is actually equatorial, whereas alpha anomer, it is axial, and that axial creates some steric strain within the cyclic ring, within the other H groups. Alright, now in the 6th ring, it will be called pyranose, and in the 5-membered carbon ring, it will be called furanose. To detect whether the end has reducing sugar, you can use Tollens or Benedict's reagents to test for the hemiacetal. Because hemiacetal is a reducing sugar, it would oxidize. So under Benedict's reagent, Benedict's reaction turns into a coppery solid, which is red, and that detects it. And Tollern's reagent detects into a silverish metal when it reacts. The chains could also be esterified, which means you can attach OCH3 to the different groups. So if this is OH, 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 they can be replaced with OCH3 if you react them with esters. They could also be formed into acetal or ketal. So if you react them with alcohol, let's say ethanol, you can switch out this OH group into an OCC because it's ethanol. And yeah, we have our monosaccharides here. These are the ones to know and remember. We have D-fructose, which is a ketohexose because it has a carbonyl carbon bonded to two C's at the very end here as the most oxidized group, and is a 6-member chain. 1, 2, 3, 4, 5, 6. It's a D-fructose. The only OH here to the left is on the top. And D-glucose is an aldohexose because its most oxidized group is a aldehyde. And the only OH pointing to the left is the second one. D-galactose, it has two OH pointed to the left, and they're in the middle one. The D-mannose has two H pointed to on the top two carbons over here. I think of it as like a man's head. When we draw stick man figures, the head is always on the top. Galactose is in the middle. Glucose only has one. And they're all three are aldohexose because they all have aldehyde as the most oxidized parts. Next we have some disaccharides. Disaccharides here include sucrose, which is glucose plus fructose in an alpha 1,2 combination. When we note down carbons, we note 1, 2, 3, 4, 5, 6 all the way around. Alpha in a carbon in an aldohexose, the carbon 1 will always be the top one, whereas in ketohexose, the C carbon will be number 2 over here. With the carbonyl carbon, it will be number 2. So basically the glucose here, number 1, will be bonded to the number 2 carbonyl over here in an alpha formation. So that is on the opposite sides. Next we have lactose, which is galactose beta 1,4 bonded to glucose, galactose over here, and in a beta connection form, they would be bonded on the same side, and the one is here, this carbon, and lactose and glucose 1, 2, 3, 4. It will be bonded to this carbon, so they will basically be stacked on top of each other. See, 1, 2, 3, 4. They will be stacked on top of each other like this. Okay. Next we have maltose, which is glucose alpha 1,4 bonded to glucose. They'll be bonded to the opposite side, so still 1, 2, 3, 4. So they will stack similarly to lactose, but the anomeric carbon is flipped upside down. Cellulose and starches and glycogen, they're all part of polysaccharides. Polysaccharides are multiple chains, more than 2. Important ones to know are cellulose, which is glucose bonded to itself via beta 1,4 connections. Starches are could be divided into amylose and amylopectin, and they use alpha 1,4 chains, or with amylopectin they also have alpha 1,6 branches coming out every 25 or more chains. Glycogen is basically like amylopectin, but there are more alpha 1,6 So more branching out. Remember, 1, 2, 3, 4, 5, 6 carbons. So that means they can branch out perpendicular way. If you have normal chains going like this, they're in 1,4 formation to be connected as such. The 6 will be branching perpendicular from it. Now, humans cannot digest cellulose, but we can digest starches and store them as glycogen for more efficiency. Beta amylase, they are used to reduce the sugar and like cleave them from the non-reducing end, and alpha amylase is just cleave randomly from reducing end to help cut the chains. Note that as humans, we also have glycogen synthase to make the glycogen, and also it will be discussed further in the later chapters about glycogenolysis and gluconeogenesis. Alright, take care.